Okay, so myself Satyanarayana, so from the trivial department. So today I want to discuss about two contents. So the first one is realization of basic gates using universal gates. The second content is implementation of a Boolean expression using universal gates. So what are the universal gates here? What are the universal gates? So what are the gates considered as universal gates? So what are the gates considered as universal gates? We have two gates, NAND gate, second gate is NOR gate. So these two are considered as universal gates. So why they are universal gates? Because with the help of these two gates, we can implement any Boolean function or you can construct any type of gate. So like you can construct AND gate, you can construct AND gate, you can construct OR gate, you can construct NOT gate, you can construct XOR gate and XNOR gate. You can construct all type of gates with the help of NAND and NOR gates. That's why the name is universal gate. So that's why NAND and NOR gates are universal gates. So here, so we'll realize the basic gates using universal gates. The basic gates are gates are so AND gate, so OR gate, and a NOT gate. AND gate, OR gate, NOT gate, they are comes under basic gates. Now how NAND and NOR gates work as AND gate, OR gate, NOT gate. We will see it one by one. Now first realization is how the NOT gate can be implemented with the help of NAND and NOR gates. Now we'll see first operation of NOT gate. So this is the symbol of NOT gate. Symbol of NOT gate. The input for NOT gate is E. So the output of NOT gate is Y is equal to A bar. So always output is complement of input variable. So I will draw the truth table here. So based on the truth table, you can understand the operation of a NOT gate. Y is equal to A bar. A acts as input variable. So Y is equal to A bar. So that is output. Always output is complement of input. So here we have single input variable. Will have two conditions, two possible combinations. So 0 and 1. We have single variable. Will get two combinations. So 0 and 1. When A is 0, so the output is 1 because Y is equal to A bar. So 0 bar is 1. So when A is 1, so the output is 0. So this is the truth table. So describes the operation of a NOT gate. Now the same operation should be carried out with the help of NAND gate. We will see it how we can implement. So while implementing, what are the input variables we are giving, what are the outputs we are getting from the NOT gate should not be changed. That means, so here in the case of NOT gate, we are giving the input as A variable. So the output of NOT gate is A bar. So the same thing should be get with the help of NAND gate. With the help of NAND gate. So I am realizing the NOT gate operation with the help of NAND gate. But in case of NAND gate, the minimum number of inputs are always 2. The minimum number of inputs always 2. But if you want to implement NOT gate with the help of NAND gate, so we need only single input. We have only single input. So but in case of NAND gate, so the requirement is 2. The requirement of input variables are 2. So how we can make it as 2 input as single input? So just by shorting the input terminals of NAND gate and provides a common point. This is the common point. For this common point, so we need to give A. Now A is acts as a common input. So both the inputs of NAND gate. So what is the output of NAND gate here? So Y is equal to A dot A whole bar. So generalized expression for NAND gate is Y is equal to A dot B whole bar. A dot B whole bar. If the NAND gate has two inputs that are A and B, so the output of NAND gate is Y is equal to AB whole bar. But here we are giving a same input to the both the inputs of NAND gate. That's why, so both the inputs are same. Both the inputs are same to the NAND gate. So the output of NAND gate is Y is equal to A dot A whole bar. So A dot A means A only. So Y is equal to A bar. So this is the implementation of NOT gate operation with the help of NAND gate operation, right? So same thing is we can construct with the help of NOR gate. Same thing is we can construct with the help of NOR gate. Again, so I'm taking the one NOR gate here. So one NOR gate. Again, in case of NOR gate also, the minimum number of inputs are 2. The minimum number of inputs are 2, but for the NOT gate, we have only single input. So due to that, I am shorting the 2 inputs of NOT gate, and I have to provide a single input. Provide single input. So the output of NOR gate is equal to A plus A whole bar. So the generalized expression for NOR gate is, so Y is equal to A plus B whole bar. The two inputs are different, so the output of NOR gate is A plus B whole bar. But here the same input is given here. The same input is given to the both the inputs of NOR gate. So the output is Y is equal to A plus A whole bar. So that gives Y is equal to A bar. Y is equal to A bar. A plus A is always A. As for Boolean laws, A plus A is always A. So Y is equal to A bar. So this is the NOT gate realization with the help of NAND gate and with the help of NOR gate. So coming to the next gate, AND gate. So next type of gate realization is AND gate. How NAND gate works as AND gate, how NOR gate works as AND gate. Now we'll see the basic symbol for AND gate is. So this is the basic symbol. So the inputs for AND gate is AB. So the output is Y is equal to A dot B. Y is equal to A dot B. So I am forming the truth table. So Y is equal to A dot B. Now here we are having two input variables. So based on input variable, we'll get 4 combinations, 4 possible combinations: 0 0. So 0 1, 1 0, 1 1. So when input is, when both the inputs are 0, so the output is 0. So if one of the input is 0, also the output is 0, because Y is equal to A dot B. If one of the input to the NAND gate is 0, so the output is 0. When both the inputs are I, the output is I. That is the conclusion here. In case of AND gate, when both the inputs are I, so the output is I. Otherwise, you can also say that when one of the input is 0, so the output is 0. So the same truth table will get with the help of NAND gate. So now first we should know that how many NAND gates are required for getting the operation of AND gate. How many AND gates are required for getting the operation of AND gate? So that is getting from the expression. So Y is equal to A dot B. Now I am changing the expression in the form of NAND gate. So how you can implement? Just I am applying the one complement over the AB. Just I am applying one bar over the AB. But when you are applying the complement, so the expression of AND gate is going to be changed. The expression of AND gate going to be changed. So already told you. So what are the inputs you are giving to the actual gate? What are the output you are getting from the actual gate? That should not be changed. So what are we doing here? Again, we need to apply one more complement. That means we are applying the double complement to the expression AB. So that we will get the expression as Y is equal to AB bar and whole bar. So both the complements, so cancel each other, we'll get Y is equal to A dot B. Now based on this expression, so we can know that how many NAND gates are required to implement AND gate. So AB bar, for representing AB bar, we require one NAND gate. For representing AB bar whole bar, we require one more NAND gate. So the total requirements are two. Two NAND gates are required. Two NAND gates required. So the first NAND gate inputs are A and B in the first NAND gate. So Y is equal to A dot B whole bar. Y is equal to A dot B whole bar. So I'm taking one more NAND gate. So for this NAND gate, so the output of first NAND gate acts as a common input to the second NAND gate. So we'll get, so Y is equal to A dot B whole bar and whole bar, that gives the operation of AND gate. So this is the AND gate realization with the help of NAND gate. So in case of NOT gate, we require only one NAND gate. But if you want to implement AND gate with the help of NAND gate, so the gates requirements are two. We require two NAND gates for implementing the operation of AND gate. So this is the realization of AND gate using NAND gate. Now the same operation is can be getting with the help of NOR gate realization. So again, so I'm getting the expression, I'm inverting the expression in the form of NOR gate. So general expression is Y is equal to AB for AND gate. Just as for the De Morgan's law, generally Y is equal to AB bar. Let us consider AB bar. As for the De Morgan's law, AB bar equal to A bar plus B bar. So by using this formula, you can easily construct the AND gate operation with the help of NOR gate. So again, same process, just I am applying a double complement over the AB. I am applying a double complement here. So based on De Morgan's law, so just I am converting the given expression into NOR form. So AB whole bar, that gives A bar plus B bar and whole bar. A bar plus B bar and whole bar. So by using this expression, A bar plus B bar. So by using this expression, we can realize AND gate with the help of NOR gate. Now how do you get A bar here? How do you get A bar from A? So already I have seen how we can realize a NOT gate with the help of NAND gate or NOR gate. Already I have seen. So Y is equal to, so I have to get Y is equal to A bar plus B bar whole bar. First you need to construct A bar. With the help of NOR gate. So I have to take one NOR gate, getting A bar from A. So this is A bar. So Y is equal to A bar plus B bar whole bar. Getting A bar from A with the help of one NOR gate. So again we need to get B bar from B. So B bar is a common input to the second NOR gate. So we'll get B bar. So A bar, B bar. Again we have to perform one more. We have to provide one more NOR gate for getting the actual expression. So one more NOR gate, that is A bar plus B bar whole bar. So the minimum requirement here, 3 number of NOR gates are required to realize AND gate with the help of NOR gate. So these are relation of NOR gate, AND gate with the help of NOR gate. So the next one. So next realization is OR gate. OR gate using a NAND and NOR gates. First we will see the how NAND gate work as a OR gate. So OR gate. So the symbol of OR gate. So this is the symbol of OR gate. The inputs are 2, A and B. So the output of OR gate is A or B or A plus B. A plus B. The truth table, always truth table indicates the operation of a gate. The operation of a gate. So y is equal to A plus B. So again we'll get 4 combinations here based on 2 variables 0 0 0 1. So 1 0 1 1. So y is equal to A plus B. 0 plus 0 0. 0 plus 1 1. 1 plus 0 1. 1 plus 1 1. Here in case of OR gate, the conclusion is if one of the input is high, so the output is high. If one of the input to the OR gate is high, so the output is high. So same operation should be get with the help of NAND gate. Again, so y is equal to A plus B here. So I am implementing the OR gate operation with the help of NAND. So again, you can use here De Morgan's law. Just apply double complements without changing the actual expression. Y is equal to A plus B, that is OR gate expression. So I want to convert the expression in the form of an AND gate. For that purpose, just I am applying a double complement over A plus B. So as for the De Morgan's law, A plus B whole bar equal to A bar dot B bar. A bar dot B bar, just substitute here. So y is equal to A bar dot B bar whole bar. So from this expression, we can realize OR gate operation with the help of NAND gate. So how to get A bar from A with the help of NAND? So a common input is given to the first NAND gate, that is A. From A, so the output of first NAND gate is A bar. Already have seen how now NAND gate works as a NOT gate. Already have seen. So the same gate I am representing here, as well as B. So this is the B input. So the output of first NAND, second NAND gate is B bar. B bar. So A bar dot B bar. We need one more complement. So again, so the outputs of so 2 NAND gates given to the another NAND gate. Another NAND gate. So A bar dot B bar whole bar. So this is equivalent to A plus B. A plus B as per the De Morgan's law. So we require 3 number of NAND gates to realize OR gate. We require 3 number of NAND gates to realize OR gate. So next one we will see how NOR gate work as a OR. So expression from expression only. So y is equal to A plus B. Just I am applying double complement. So based on this expression, we can realize OR gate operation using NOR gate. So the here 2 number of NOR gates are required for representing OR gate operation. So A plus B. A and B are the inputs to the first NOR gate. So the output of first NOR gate is A plus B whole bar. But we need to get, so the operation as A plus B. For getting, we need to use one more NOR gate. A plus B whole bar that gives A plus B. That gives A plus B. So we require 2 number of NOR gates to realize OR gate. So next topic is implementation of Boolean expression. Implementation of Boolean expression using universal gates. So implementation of Boolean expressions using universal gates. So first we will see how we can convert. How we can convert from AOI logic to an AND circuit. So we have to follow these steps. First step is based on the given expression. Based on the given expression, so design a circuit with the help of basic gates. That is AOI gates, that is AND OR inverters. Based on given expression, so construct the expression with the help of AND gate, OR gate, inverter. That is the first step. How to follow that. Second step is apply bubble. If you want to implement the same expression using an AND gate, so second step is apply bubble to the output of each AND gate. Apply bubble to the output of each AND gate. So apply bubble to the input of OR gate. This is the second step for getting the entire expression in the form of NAND gate. So third step is apply NOT gate. Apply NOT gate where we are adding the bubbles in the previous step. Second step is you have to add bubble to the output of AND gate and add bubble to the input of OR gate. So third step is where we are adding the bubbles. So for compensating that bubble, so we need to use one more complement. So that is done with the help of NOT gate. That is the step 3. So step 4 is I have to identify, I have to check where double inversions are exist in the circuit. So that double inversions are can be eliminated. That is the fourth step. Last step is how to deal the final circuit. So they are the steps we need to follow. So while constructing any Boolean expression in the form of NAND gate. Now we'll see one problem. So based on this, this is the expression. So this expression is implemented with the help of NAND gate. So F is equal to AB plus C dash D. So first step is, so based on given expression, we have to draw the circuit with the help of basic gates. So AB, so A is the input. We have 4 inputs here. A, so B, C, and D, 4 inputs. So for representing AB, we require one AND gate. So AB, first AND gate. So C dash D, but we have C variable. So for getting C dash, so we have to use one NOT gate here. C dash into D. So we have to use one more AND gate that gives C dash D. C dash D. Now to do the sum. To do the sum with the help of OR gate. To do the sum with the help of OR gate. That is F equal to AB plus C dash D. AB plus C dash D. So this is the AOI logic circuit diagram. So based on given expression, so we need 2 AND gates, 1 OR gate. So this is the AOI logic circuit diagram. This is the step 1. So step 2 is so where we are having the AND gates. So you need to identify where we are having the AND gates. So add bubble to the output of each AND gate. Add bubble to the output of each AND gate. Add bubbles to the output of each AND gate. Add bubbles to the input of OR gate. So this is the second step. The first step is how to draw the AOI logic circuit diagram. The second step is, so we need to identify the basic gates like AND gate, OR gates, where are having. So always add, if you want to implement the circuit with the help of NAND gate, add bubble to the output of AND gate. So we have 2 AND gates here. Add bubbles to the first AND gate and second AND gate, and we have 1 OR gate. So add bubble to the at the input side of OR gate. At the input side of OR gate. But what happens here? If you're adding the bubbles, definitely the expression going to be changed. The expression going to be changed. So that's why I have to follow the third step here. What is the third step? Where we are adding the bubbles. Where we are adding the bubbles. So by compensating these bubbles, we are adding one more inverter. One more inverter with the help of NOT gate. With the help of NOT gate here. So I am adding one bubble here for compensating the output of NAND gate here, output of AND gate. Here, so here for compensating this bubble at the gate 1, so I am adding one inverter here. again at the second also, just compensating this bubble, I'm adding one inverter, as well as we're adding bubbles to the input side of OR gate. For compensating these bubbles, again I have to add one more. So one more bubble. One more bubble. So this is the start step. Third step is, so for compensating the bubbles which are placed at the respective gates that should be compensated with the help of NOT gates. So next step is, so I have to identify where you are having the double inversions. Where you are having the double inversions, that inversion can be eliminated. So these two are double inversion, these two also double inversion, these two are removed. These two are removed. These two are removed. So now, so this is the one NAND gate, second NAND gate. So the bubbled OR gate is equivalent to the NAND gate. The bubbled AND gate, the bubbled OR gate is equivalent to the NAND gate. So instead of bubbled OR gate, we can replace with an AND gate. So the operation is exactly same. The bubbled OR gate operation is equivalent to the NAND gate. Equivalent to the NAND gate. Now, so three gates, two AND gates, one OR gates are replaced with now NAND gates. But we are having one more gate here, NOT gate. How we can replace NOT gate with the help of NAND gate? Already I have seen the realization. So instead of inverter here, we can place one NAND gate here. One NAND gate. So NAND the same input. C is a common input to this NAND gate. We will get C bar. Now the total circuit is so composed of only NAND gates. So this is the realization of given Boolean function using the NAND gate. So now we'll see how we can implement a Boolean expression using the NOR gate. So the process is almost similar. So again, what the first step one is based on the given expression, how to draw the AOI logic. Second step is, so in case of an AND implementation, where you are having the AND gate, how to add the bubble at the output of each AND gate, as well as input of OR gate. But here, so reverse process you have to follow. In case of you want to implement this expression with the help of NOR gate, the second step is where you are having the OR gate. Where you are having the OR gate, you have to add bubble to the output of each OR gate as well as input of AND gate. The process is just reverse. Reverse what I have done in case of NAND implementation. In case of NAND implementation, we are adding bubble to the output of each AND gate as well as input of each OR gate. But in case of if you want to implement expression using NOR gate, that add bubble to the output of OR gate and inputs of AND gate. That is the process I have to follow here. Third step and fourth steps are similar. So first step is from the given expression, draw the AOI logic circuit. Again we have three inputs here, three inputs. So A, B, C. A, B, C. So AC and B. AC is the product term. For representing product term, so we are taking one AND gate here, AC. Again, second product term is BC dash. Second one is BC dash. So this is the C. This is the C, but we need to get a C dash. For getting C dash, we are using the one NOT gate here. So this is B. So we'll get BC dash expression. BC dash expression, AC and BC dash. But to do the sum here, for doing the sum, I have to use the OR gate here. I have to use the OR gate. So F is equal to BC dash plus AC. BC dash plus AC. This is the AOI logic circuit. and or inverter logic circuit. This is the first step you have to follow. From the expression you have to draw the expression with the help of basic gates. Second step is, so where you are having the OR gate, add bubble to the output of OR gate, add bubble to the output of OR gate, add bubble to the input of AND gate, add bubble to the input of AND gate. This process is reverse. So here in case of NOR implementation, how we are getting the NOR from OR? Just add bubble to the output of OR gate, that gives a NOR operation. That is the reason here we are adding the bubble at the output of OR gate and inputs of AND gate here, because input bubbled AND gate is nothing but a NOR gate. Bubbled AND gate is nothing but a NOR gate. That's why adding bubble to the input side of AND gate, adding bubbles to the outputs of OR gate, right? So that is the second step. Second step is add the bubble to the respective gates. Now third one is, when you are adding the bubble, the expression is going to be changed. The expression is going to be changed. So but we need to get same expression. For getting the same expression, where we are adding the bubbles, so we have to, for compensating the bubbles, we are adding one more inverters. So in this fashion, we are adding bubble at the input side of AND gate. So add inverter here for compensating the bubble that is added to the input side of AND gate. Right, likewise. So adding bubble here, so I have to add one more inverter here. BC. Now add inverter at the output side of the gate here, because we are adding bubble to the output of OR gate. For compensating this bubble, I am adding inverter. So this is the third step. So wherever we are adding the bubbles, so at the corresponding places I have to add NOT gates for compensating those bubbles. Now next step is I have to identify the double inversions in the line. I have to identify the double inversions. The double inversions are eliminated. Because why I am eliminating here? Because double component will get the same expression. So two inverters connected in a series connection. Suppose if you are giving one as input to the first NOT gate, so the output of first NOT gate is 0. Again 0 acts as input to the second NOT gate, so the output of second NOT gate is 1. So same expression will get here. What are the input we are giving first NOT gate? So the output of second NOT gate is same as input of first NOT gate. That's why you can eliminate these inversions. So that is the third step, identify double inversions that can be eliminated. So this one inversion is eliminated. So the resultant circuit is, after eliminating the double inversions, F. So now, so next step is you have to replace bubbled AND gate with NOR gate. So the bubbled AND gate is same as NOR gate. Just have to replace bubbled AND gate with NOR gate. bubbled AND gate is same as OR gate. OR gate. Now, so one more gates we are having here, NOT gates. NOT gates. So NOT gates are realized with the help of NOR gate. Already have seen, instead of inverter here, so inverter is realized with the help of NOR gate. Already have seen. As well as we have at the output side we have a NOT gate that can be replaced with a equivalent NOR gate. Equivalent NOR gate. So this is it. So this is the realization of given function using NOR gates. So here one more thing. So why we're constructing with the help of NAND and NOR gates. Suppose if you want to implement the same expression with the help of basic gates, we require AND gates and NOR gates and inverters. We require three types of ICs. So AND gate IC, OR gate IC, and NOT gate IC. But the same expression is implemented with the help of NAND gate. So all gates are same type. All gates are same type. So that is the requirement of IC is very less. The requirement of IC is less as compared to the A-wise logic. That's why we are constructing all the Boolean expression with the help of universal gates, either NAND or NOR gates. The IC requirements going to be reduced as compared to the basic gates. So if you're implementing the same expression with the help of AND OR inverter, we require three gates, three ICs, AND IC, OR IC, and NOT IC. But the same expression can be implemented with the NAND and NOR. But all the gates are same type. All the gates are same type. So single IC package is enough to represent or to realize given function. That is the advantage of representation of any function with the help of universal gates. Thank you. Assignment, I will assignment problems solve. So there are the assignment problems. So to submit by not before a specified time period, I will send the Google link. So you have to upload the assignments in Google link. So the assignment problems, 4 problems I have given based on what I have discussed. So I have to submit another before given time. Thank you.